Off here, that's okay. All right, so in chapter 7 through 9, we studied simple linear regression and calculated equations in the form y hat equals a plus bx. Again, on the AP exam and on the formula sheet for AP, which you're going to get one pretty soon, and we want to start working with it in the context of lots of different problems, and so you need to learn to recognize the formulas and what they go with. So on the AP exam, it'll say like y equals b sub 0 plus b1x. Okay, they just use, instead of a, they use b sub 0, and instead of b, they use b sub 1. It's the same exact thing, just different letters. That's all. Okay, so that's a regression. The way we get to that on our calculators, we do stat calc 8. It's the same either way. It's the same thing regardless of the variables that you use. So since this equation was based on a sample, it is subject to sampling variability and probably incorrect. Okay, so our regression line, we're talking about the conditions, and I guess here I'm trying to give you a reason why we have to check the conditions that we do. So this might seem a little complicated what we're talking about here, but it's not something you have to talk about for every condition. So this is just kind of a why, and then we'll get to the actual conditions that we need to check, or the things we need to state when we are dealing with a test for a slope of a regression line. So since this equation, we got this equation based on sample data. So that means this equation is probably not completely correct, right?
Please pardon this interruption. I just want to get the students that...
All right, so does it make sense that this is not correct? We got our data from samples.
Yeah.
So in other words, if we're trying to use this equation to correctly represent a relationship between fat and calories in burgers, since we just took sample data and wrote this equation, it's probably not the true linear relationship between all fat and calories in sandwiches. So it's still our best guess. So we use this guess, this estimate, this guess to estimate the true regression line, alpha plus beta x. Alpha is the true y-intercept, beta is the true slope. Now all we are testing on in AP Stats is the true slope. Our linear regression t-test that we've talked about for the last 2 lessons, confidence intervals t-test, we're only doing it for the slope. Okay, we could do it for the y-intercept too, but it makes sense, the most sense to do it for the slope, because that describes how steep the line is. So one of the assumptions in regression is that the true regression goes through the mean y value for each value of x. Okay, when you write a linear regression, the regression line always goes through x bar comma y bar, which we did discuss a long time ago. I'm just refreshing your memory. Every regression line goes through the mean of the x's and the mean of the y's. So you take all the x values and find their average, and all the y values and find their average. That point is on every regression line. Okay, so the y hat value, the y hat is the value you get on the least squares regression line, produced by the model, has 2 interpretations. Y hat is the average y value for a particular x value. So sometimes you could write the regression equation as the mean of the y's is equal to alpha plus beta x. Also, another interpretation is that y hat, the predicted y's, the y hat are the ones on the least squares regression line. That's where the y hats are. Is the predicted y value for one particular value of x. This, in other words, the y value we get from here is the best guess for the value of y. So those are 2 interpretations for the y hat on our least squares regression line. Thus, we use the equation y equals alpha plus beta x plus e to describe the general regression model. General regression model. We'll talk about e in a second here. The actual y value for a particular value of x is based on 2 terms. The mean value of y for that particular value of x, and a random deviation from the mean, E. E is like an error, okay? If the error term was not included, that would imply that all points would fall exactly on the true regression line. Okay, so another one of the assumptions of this regression model is that E, the errors are the error is normally distributed with mean 0 and standard deviation of the errors, which we estimate with the standard deviation of the residuals for all values of x. So here's what we have to consider. Okay, I think this picture, it kind of summarizes what we're dealing with here as far as assumptions. We are assuming, well, not what we're assuming, here's factual. For every x value that I have, isn't there an entire distribution of y values that I could get for that x value? And if we think of the mucus example, remember the mucus, and they each got 0, 1, 2, 3, or 4 glasses of milk. So for one glass of milk, there were 3 different people who had that, right? 3 different people who had 1 glass of milk. So we automatically, above that x value, had 3 dots right above that particular x value. And in reality, there's an entire infinite possibilities for the y values for each individual x value. So for every individual x value that you're dealing with in your linear regression, there's an entire distribution of y values available for it, because it's a scatter plot. So we have to assume, the assumption is that every one of these, where there's dots, all these possibilities for y values for each x value, we have to assume that all of these possible dots are normally distributed. So we're assuming, and E, the error that we're talking about, is kind of like a residual. Okay, here's our least squares regression line right here, least squares regression line, and here's our different data values. They are different distances from that least squares regression line. That's like your error. That's what you have to add to the general regression equation in order to make it all work out, to fit your statistics, your estimation. This is, remember, alpha and beta are the true. What's the true relationship between the x and the y? We'll probably never know that. Okay, that's why we have to talk about the conditions and check the conditions. So that's what we talk about right down here. Each value of x has its own distribution of y values. And we have to assume that the distribution for every y value is normally distributed with the mean of alpha plus beta x. The average is the y value you get from plugging it into the true line, and the standard deviation is the standard deviation of the residuals. Residuals having the same effect as an error. A residual is the amount of error. How far off is our observed from our expected? Alpha plus beta x is the mean value of y for that particular value of x. So, you know, here's that value of x. I have all these different possible y values. It's just adding all those y values up and averaging them. So thus, when we do inference for regression, we will need to check that the linear model is appropriate. The variability of the residuals is the same for all x's, and that the residuals are approximately normally distributed. In other words, these are going to be some of the conditions we need to check. All right, again, remember, this is just an explanation of why we need to check the conditions. You're never going to have to draw little pictures like this when you check conditions. I guarantee you that.
Do you have Hannah Rose fill this out when she has time?
Okay, so for example, suppose that we knew alpha was 2, beta was 5, and the standard deviation of the errors was 1.3. On the wrong page. Okay, that would mean our regression equation, general regression, y equals alpha plus beta x plus e. This comes from the other side that we just talked about. This was, nope, it's true value. Okay, This is y. The true regression, alpha and beta are the true values of the slope and the y-intercept, and e is the error. And they're telling us that alpha is 2, so I'm going to replace the alpha with 2, the beta with 5, and the e with 1.3. So if x equals 3, if x equals 3, wouldn't we just plug 3 in there for x? So then I'd have y equals 2 plus 5 times 3 plus 1.3, so that's 15, 17. So y would be 18.3. So when x is 3, y is 18.3, okay? Or y would be 17 with a standard deviation of 1.3. So it would be 17, give or take 1.3. Give or take. So it could be plus 1.3 or minus 1.3 actually. What?
So the answer is yes.
There's not a question. Nope, this was an example. Okay. So now, if x is 4, estimate the probability that y is greater than 23.2. Okay. So now this does ask a question here. So if x equals 4, what should y be? Well, y should be approximately normally distributed. And I guess the same thing up here. We could write the same notation. Let me back up to this one. Y would be approximately normally distributed with a mean of 17 and a standard deviation of 1.3. Okay, that's when x is 3. If x is 4, y would be about 2 plus 5 times 4, or 22, with a mean of 22 and still a standard deviation of 1.3. So now we want to know what's the probability that y is greater than 23.2. So that would be the same as the probability that that's really, I guess that's all we need. We don't need to write another probability statement. Y should be normally distributed. So from here we can just say, well, if it's normally distributed and looks like this, a mean of 22 and a standard deviation of 1.3, that would be 23.3. So here's our normal distribution. We have a mean of 22, standard deviation of 1.3. What is the probability that it is, here's 23.2, greater than that? So that's where we can just go NCDF. The lower bound of this shaded region is what? 23.2. The upper bound is infinity. The mean is 22 and the standard deviation is 1.3. So then we go to our calculator, second distribution, NCDF.
Do you have to draw a picture every time?
I would.
I didn't know since they said we're supposed to.
Well, yeah, assuming it's normal is why we can use NCDF. You should draw the picture, because this will also help you figure out your lower and upper bound if you ever struggle with that. So my probability, when I do NCDF, the p-value, the probability is 0.177 or 0.1780 if you round it. So there's a 17% chance that when x is 4, it'll be actually greater than 23.2.
Wouldn't it be 23.3?
No, it's normal. We don't worry. That's only in binomial, then you go. They're asking about 23.2. That's what they're asking about. This is where the standard deviation goes based on the definition. So if x is 5, the middle 95% of observed y value should be between which two numbers? So this is a little bit different.